Welcome back to part 2 of this lesson. We are now looking at properties of logarithms, expanding and condensing. So quick refresh for our 3 of these exponent properties that we looked at, our power rule, our product rule, our quotient rule, and our power rule. These are related to our log properties because exponents and logs are inverses of each other. If I have a log and inside that log what I'm evaluating is the product of 2 terms, I can split that up into the sum of 2 logs, 1 for each term. And if we relate that back to our product rule, when I'm multiplying like terms, I add their exponents. When I'm multiplying like terms, I add their exponents. If I have division within the log that I'm evaluating, I can split that up into the subtraction of the 2 logs. When I'm dividing like terms, I subtract their exponents. When I'm dividing like terms, I subtract their exponents. And lastly, if I have an exponent within what I'm evaluating, I can bring that to the front and multiply it by the rest of my logarithm. When I raise a power to another power, I multiply my exponents. If I'm raising a power to another power, I multiply my exponents. So we can use these 2 ways. We can use them to break our logarithm apart, or we can use them to consolidate into a single logarithm. First, we are going to practice with expanding. On the first one, I have log base 3 of 11x. This 11x means 11 times x, so that is multiplication. So I can split this up into log base 3 of 11 plus log base 3 of x. On the next one, log base 5 of x to the negative 2. This is an exponent, so I can bring it to the front, and this will be negative 2 times log base 5 of x. Moving on to C, I have a radical. I didn't have a rule that dealt with radicals, but I know how to rewrite this as an exponent. That would be x plus 1 to the 1/3. And I do have a rule that deals with exponents. I can bring this now to the front 1/3 and multiply it by the remainder of my log. On D, I have, again, another radical, so I'm going to rewrite this as an exponent. And I can bring that to the front 1/2 times natural log of x times x plus 2. This is also now multiplication within here, so I can split this up again into natural log of x plus natural log of x plus 2. And that 1/2 needs to apply to both logs. So what I can do is leave it like this, indicating that there would be distribution, or I can distribute it out and put that 1/2 in front of both logarithms. And the reason for that is both of them were inside my radical, so I need to make sure that if I were to consolidate this back, I would know to put both terms in the square root. Okay, last one. We've got 3 things going on here, starting with the a to the 3rd. That would be 3 times the natural log of a. That's being multiplied by the natural log of b minus 4, so I can add natural log of b minus 4. Then I have a denominator here, so that means I can subtract. This one also has an exponent, so I can bring that 2 to the front, and that will just leave me with natural log of c. All right, we are going to do this the other way around now. We're going to consolidate into a single log expression. Starting on a, I have 4 natural log of b. That means the 4 was originally an exponent, so that would be the natural log of b to the 4th power. On b, we've got 3 things. We'll go one at a time. I'm going to have natural log, 1 log. The 2 natural log of x means that this was x squared. That's being added here, so I know I'm going to multiply by whatever the next term is. And if it's 3 natural log of y, that means that it was y to the 3rd. And then finally, subtraction means that I would have divided by z. So there's my single log. Moving on to c, I have 1/2 log base 5 of x. So that would convert back to square root of x. And if these 2 are being added, that means that the terms were being multiplied. So that's going to be multiplied by x minus 3. And then on the last one, I have 1/5. That means this is going to have been the 5th root of x minus 3. Then the next 2 are both being subtracted, so that means that they are both going to go in the denominator. The 2 means that this was x squared. The 3 means that this was being raised to the 3rd power. And there's my final condensed logarithm. We're now going to move on to the last part, or last page. The first part of this page, we are looking to see if these log properties were used correctly. Did we expand or condense properly? So starting with A, If this was to the 5th power, that means I would need a 5 on both of them, which is correct because I have a power of a product or of a quotient here. And then because they were being divided, I could split that up into subtraction. So this one was done accurately. On B, I had multiplication, and it looks like they turned this into the product of two logarithms, which is incorrect. This would need to be the sum of those two logarithms. Looking at the next one, they consolidated. This would become x to the 4th. Great. And then these are, this negative is being subtracted. They would both be, this negative is being distributed. They would both be subtracted, which means both the 3 and the y go in the denominator. So that is correct. On the next one, this doesn't even look like log properties. They just decided 6x was equivalent to 6 plus x, which is not correct. And then the next one, at first glance, okay, they did 5, 2, but where did this 1 come from? Let's look at if I were to expand this out by hand. I would have 5 log of x, great, plus 2 log of y, great. And then that 10 in the denominator would tell me that I could subtract log of 10. Now, what is log of 10? Remember, this means if there's no base written, we're assuming it's 10. 10 to some power equals 10. Well, 10 to the first power is 10. So that means that log of 10 is equivalent to 1. So they had that minus 1 at the tail end, so they did this properly. That is true. So with that in mind, we are going to do some expansion and determine how that applies to transformations of our parent functions. So if I have log base 2 of 8x, I can expand that out into log base 2 of 8 plus log base 2 of x. Now, what is log base 2 of 8? This is saying that 2 to some power is equal to 8. Well, 2 to the 3rd power is 8. So that means that log base 2 of 8 is 3. So this could be expressed as log base 2 of x plus 3. So if I was going to compare this to my parent function, this means that I have applied a vertical shift up 3 units. Looking at B, I have natural log of x squared. So using my exponent properties, I could bring that exponent to the front and rewrite this as 2 times the natural log of x. Well, comparing that to my parent function, this means that I applied a vertical dilation by a factor of 2. Okay, and then lastly on C, I have log base 2 of 3x plus 12. Now, as this is currently written, there's no properties I can apply. I don't have multiplication, division, or an exponent. But if I look at 3x and 12 more closely, they have a common factor of 3. If I factor out a 3, that's the same thing as x 3 times x plus 4. So by factoring, I now have multiplication, and I can rewrite this as log base 2 of 3 plus log base 2 of x plus 4. Now, what is log base 2 of 3? That means 2 to some power is equal to 3. And that's not going to be a whole number or a pretty number. That's going to be like 1 point something. I would need a calculator to evaluate it exactly. So what I'm going to do is leave it in this form, but we know this is a number. That's going to be important. So I have log base 2 of x plus 4 plus log base 2 of 3. So if I'm comparing this to my parent function, starting with just the x plus 4, well, that tells me that I am horizontally shifting, excuse me, to the left 4 units. And this is a typo. It's not a vertical dilation. By adding this, this means that I am applying a vertical shift up whatever this value is, 1 point something units. So whatever log base 2 of 3 units would be. So it's great if it works out to be a whole number. We can say exactly how much it's being shifted, but if not, we would just leave it exactly in log form to be precise. And that wraps up our log property notes.